Do you want to learn how to apply the basic nodal analysis in circuits with independent sources? Do you want to learn how to deal with current sources when using Nodal? This video tutorial is for you. Hi, I'm Dave Wadas and I'm here to discuss how to use nodal analysis in analyzing networks with two or more sources. In this video, I will be solving two problems using the basic nodal analysis. Now, these are the two networks that we will be solving in this video. The first one is a common three-branch network with two independent voltage sources. The other one is a four-node circuit with two independent current sources. Current sources are intimidating, especially for those who are new in the circuit analysis. I will show later that these type of sources are actually easier to deal with than voltage sources, especially in nodal method. Thus, there is no reason to get intimidated. Okay, let's try this problem. So we are asked to solve for the current in each branch of the network shown on your screen. Okay, so first thing first, we need to count the number of nodes. So the nodes that it refers in this method is that those nodes with three or more branches connected to it. So in this problem, we can actually have a node here. Uh, there can be node here, right? Right. We can have a node in here, right here, right here, right here, right here, and here, right? But the node that uh, is referred in the nodal analysis are those nodes with uh, three or more branches connected to it. Okay, so that means this node right here, this node right here, and this node right here. Okay, so uh, this node right here and right here. Okay, now there are two nodes, meaning there are two nodes in this problem. So that's it for step one. For step two, we need to designate a reference node. So you can choose any of these two as your reference node. But as for me, I'll I have the in my practice I'll be always choosing this part, the bottom part. So I am assigning this one as reference node, right? So this is part right here as zero voltage. Okay. Then of course the rest of the node we only have one. This one will be labeled as nodal voltage, or maybe we can call this one our V1. All right, this is our V1. Okay, so this V1 right here is measured uh, in reference to your reference node, or with respect to your reference node. Okay. So step four, we assume branch currents for each branch. So we have three branches. So this is the first one, second one, and the third one. So I assume we have a right, we have branch current here going in that direction. Another branch current here going in that direction. Another branch current here going in that direction. So we have like I will label this one with I1, right? This will current with I2, this one with I3. Okay. So that's for step 4. Now, for step 5, we will be writing the KCL equation for each branch and then express that KCL equation in terms of nodal voltages using the head to tail, head minus tail over resistance expression. Okay, so this is quite a common practice for nodal. So step 5, so we need to write KCL equation. So we only have one non-reference node, so we only need to make just one KCL. So step 5, KCL here, non-reference node. So KCL at node 1 or node V1. So current entering equals current leaving. So that's basically I1 plus I2 is equal to I3, right? Okay, so that's half or part of our step 5. So we need to express I1, I2, and I3 in terms of the nodal voltage V1. Okay, so using the tail minus head over resistance method. So if you notice, we have I1 here. Its tail is from the 48 volts. It's going into the node V1. So if this is a nodal voltage here, V1, there is positive actually here, and the negative is right here. So if we take a loop from this point up, going into the 48 volts in this direction, we can actually say that I1 using I1 will be equal to tail. The tail is 48 volts minus head, which is V1. It's going into V1 over the resistance, which is 5 ohms. All right. And similarly, we will have I2, I2 here, which is equal to 40. That's the tail where your arrow, the tail of your arrow is from 40 volts. Then it's going into V1. Your arrow is going into V1. Your arrow, the arrow of your current, I mean, over 2. Similarly, again, for I3, we have, for I3, tail. The tail of the arrow the arrow is from V1. It's going into the reference node, which is 0. So V1 minus 0 is the numerator, or V1, all over 10. Now, these three equations right here, this I1, wait, and we have your I2, okay, uh, your I2 and for I3, you can actually substitute these three expressions in this equation. So you will get, of course, this equation right here, I1 is 48 minus V1 over 5 plus I2, which is 40 minus V1 over 2 should be equal to V1 over 10. Okay, so we have a system of equation with one variable only. One variable because we only have one nodal voltage, and that is V1. Okay, we only have one nodal voltage because we only have two nodes. One was chosen as the reference, and the other one was the nodal voltage V1. Okay, so if we will try to solve this system of linear equation, we will get V1. Your V1 is equal to 37 volts. Okay, so you will use a um, voltmeter. You have, and you will use your probes right here and here. You will get 37 volts. So the voltage between this node and this node is 37 volts. Okay. So meaning we can solve for branch currents now. Okay. So here, branch currents. Okay. So we can have I1 actually because we already have V1. So from this expression right here, we can have our I1 equal to 48 minus 37 over 5, or is equal to 2.2 amperes. You have I2, which is equal to 40 minus V1, which is 37 over 2. So that's 3 halves, or 1.5 ampere. I3 is equal to V over 10. So that's 37 over 10, which is equal to 3.7 ampere. Okay. So this example was already solved using Kirchhoff's law during our previous video. So we got the same number, we got the same branch current of 2.2, 1.5, and 3.7 amperes. So if we notice, so we can check this solution. Okay, so if this current right here is 2.2, this is 2.2 volts. I mean 2.2 ampere, and this right here I2 is equal to 1.5 ampere. So 2.2 going into the node, 1.5 going into the node. Of course, your I3 should be 3.7. 3.7 is the sum of 2.2 and 1.5, and that's one way of making sure you get the right numbers. It's one way of being confident that you have uh, you have done the right solution. Okay. Okay, let us solve sample problem number two. So for sample problem number two, we are asked to calculate the current in each branch of the network shown on your screen. So in this network, we have 7 branches. So 2 branches for each current source, and we have 5 branches for each resistor. So basically, we are asked to solve for 5 branch current here. Okay, so let's start. So step one, we need to count the number of nodes. So the number of nodes we are referring to are those nodes with 3 or more connected branches. Okay, so I can see we have a node here with 3 branches connected right here. Another node here with 3 branches connected also. And we have a node here with 4 branches connected, right? This one right here. And finally, we have this big node here with 4 branches connected as well. So we have 4 nodes with 3 or more branches. Okay, so that's very important. That's step one. Okay, so in step two, we need to designate a reference node. One of these 4 nodes will be designated as reference node. Now, for in my practice, no, I usually use the bottommost part of the network as the reference node, if not specified in the problem. So usually I put my reference node here. This will be my reference node. Okay. So That's it. The rest of the three nodes will be labeled or will be called the nodal voltages. So I will call this one our V1. This will right here. This will be our V1. This will be our V2. And this will be our V3. Okay. So that's step number three. Right. For step number four, which is I actually uh, mentioned that it is not practiced in many tutorials and textbook. So I will put I1 here, I1 for 1 ohm. So this will be our I1. This will be our I2 going in that direction. This will be our I3 going downward. I usually assume those branches connected to a particular to the reference node. I mean, I usually put the direction of the current going into um, the reference node for easier calculation or volt making of equation. So of course we have our I4 here for your 4 ohms, and of course we have our I5 here. All right. So that's it for step number four. So we have our current direction and label I1, I2 to I5. Okay. So for step number five, we need to write the KCL equation for each non-reference node. Okay. So we have three non-reference node, node 1, node 2, and node 3. So we write the KCL equation. So we'll start with node 1. So KCL at node 1. We have at node 1, all currents are leaving. Nothing is, no current is entering the node 1. So we have I1, right? So we have I1 here plus, of course, I2 plus 3 is equal to 0. All right. So that's our KCL equation for node 1. At node 2, we can have our KCL also. We have in here, I1 is entering, I3 and I4 are leaving. So we can have I1 is entering equal to leaving, which is I3 and I4. All right. Then for node 3, we have, so for node 3, we have three currents entering, I2, I4, and 7 ampere. I5 is leaving. So we can have I2 here plus I4 plus 7 is of course equal to I5. All right. All right. So that's half of step number 5. So we need to express this KCL current equation in terms of the nodal voltages V1 and V2. How? So we need to express every current in terms of the nodal voltage using the tail minus head of a resistance. So tail minus head of a resistance works with nodes like this where there is no supernode. So a supernode is a node between a voltage source between two nodes with no resistance. So that's another topic. So for problems like this we can use tail minus head over resistance. Okay. So for instance, if you want to solve for I1, you look at the arrow. Remember that you arbitrarily choose arrow to be going to the right. But here you can use that direction. So you have I1 for example. The arrow is from V1, so that's tail. It's going into V2, so that's V1 minus V2 over the resistance is 1 ohm. Okay, as easy as that. So if you want to solve for I2, I2 is equal to, you look at current I2, its tail is from V1, it's going into V3. The resistance between V1 and V3 is 2. Alright, if you want I3, similarly, you have I3 is right here, so that's V2. V2 minus, it's going into the reference node, so that's 0. So that's only V2, right? V2 over 3. Alright. You want I4, I4 is equal to here. I4 tail is from V2, head is going into V3 over 4. Alright. And if you want I5, I5 is equal to tail, which is V3, minus head, which is the reference node, that's 0 over 5. Okay, so basically we have all 5 current in terms of the nodal voltages V1, V2, and V3. Now if we substitute this expression, these equations in the KCL equations, we can have actually this equation right here. This will become I1, that's V1 minus V2 over 1 plus I3. I3 is V2 over 3, V2 over 3, right? I2, by the way, this is I2, so sorry, that's I2, so that's V1 minus V3 over 2, alright, this is 2 right here, V1 minus V3 over 2, plus, this is I2, I1 plus I2 plus 3 is equal to 0, alright, this expression right here, I1 is equal to V1 minus V2 over 1, it should be equal to I3, I3 is equal to V2 over 3 plus I4. I4 is V2 minus V3 over 4. Alright, so this is the new expression for your KCL at node 2. Alright, okay. And finally, we have our expression. This expression right here will become I2, which is V2, no, V1 minus V3, that's I2 over 2 plus I4, which is equal to V2 minus V3 over 4 plus 7 is equal to I5, which is V3 over 5. Alright. So we have 3 equations now in terms of the 3 nodal voltages V1, V2, and V3. So of course we don't need the 6 step or step 6 because we don't have any um, dependent source in our network, so we go directly to step 7, or we need to organize these 3 equations, 3 unknowns, into just uh, simpler equations. Okay, so we're here at step number 7. We need to organize our equations so we can use our computing devices such as calculator and computer. So well, of course we can use um, substitution and elimination method, but when we are allowed to use our calculator, we can use maximize it, no? So we can use the equation function. So what we need to do now is to, and this is what I usually do uh, when solving equations. I don't make so many modifications to the equation. I deal with fractions if always, no, always if it is better to do with better to deal with it with fractions because we don't risk truncation error. Okay, so I don't usually make multiplications as well, like LCD, GCF, and so on. So I literally use fractions. Okay, so here it is. So what will I do, for example, in this equation right here? So I will simplify it. This will be v1 minus v2 plus v1 over 2 minus v3 over 2 plus 3 is equal to 0. Now, next step is to combine similar terms. So, of course, we have v1 here and v1 here. We have two v1s and one v2 and one v3. So I will combine v1. So that's basically v1 times the coefficient 1 here and 1 half here. So that's 1 half, of course, minus v2 minus v3 over 2. I'll transfer the constant to the other side so I could use the calculator. Okay. Now, what will happen? This will become 3 halves of v1 minus v2 minus uh, 1 half of v3 is equal to negative 3. And this will be our equation number 1. Okay. Now, next next expression is this one. I'll do a similar process. So, v1 over 1 or v1 then minus v2 should be equal to v2 over 3 plus, of course, v2 over 4 minus v3 over 4. So I'll transfer every term here to the other side. So it will become v1 minus v2 minus v2 over 3 minus v2 over 4 plus v3 over 4 should be equal to 0, right? So notice we have three terms with v2 right here, one for v1 and one for v3. So we can combine this one. So we have v1 minus v2. So since we have a minus here, everything is minus. So we can add up the coefficients 1 plus 1/3 plus 1/4. So that's basically, if you notice, I'll just combine everything here. These terms right here in the middle. Plus v3 over 4 is equal to 0. Right. So, of course, this will reduce to v1 minus 1 plus 1/3 plus 1/4 is 19 over 12. So that's 19 over 12 of v2 plus 1/4 of v3 is equal to 0. And this will be our equation number 2. Okay. One more equation. So, same process. We have v1 over 2 minus v3 over 2 plus v2 over 4 minus v3 over 4, right? Plus 7 is equal to v3 over 5. All right. Now, what do we do with this with expressions like this? So, we usually transfer this constant to the right side and this variable to the left side. So, Alright, this will become V1 over 2 minus V3 over 2 plus V2 over 4 minus V3 over 4 minus V3 over 5, right, is equal to negative 7. Okay, so notice we have three expressions for V3 now, one for V1 and one for V2. So basically we have 1/2 of V1, then plus 1/4 of V2. This term right here, this term right here is for V1, minus V3 times quantity. The coefficients are 1/2, and we have 1/4 and 1/5. So we have 1/2 here, we have 1/4 here, and 1/5 here, plus 1/5 is equal to negative 7. So of course we have a negative here because every V3 terms with V3 are negative. So finally we have 1/2 of V1 plus 1/4 of V2. This is V2 right here, minus 19 over 20. So 1/2 plus 1/4 plus 1/5 is 19 over 20 of V3 is equal to negative 7. Alright, this will be our equation number 3. Alright, we are now at step 8. So we already have the three equations of nodal voltages V1, V2, and V3. Of course, you can use your calculator or your computer to solve for this system of linear equation. Three equations, three unknown. So as for me, I have used my calculator and I get these voltages 5.235 for V1, 5.118 for V2, and 11.471 for V3. So uh, the next step is to solve for the currents. Okay. So finally, for step 9, we can now solve for currents with our nodal voltages known. So remember, we have our nodal voltages obtained, our branch current obtained from tail minus head over resistance. So basically, we have our I1, which is equal to um, V1 minus V2 over 1 ohm. So V1 is 89 over 17 minus V2, which is 87 over 17 all over 1. So basically our I1 is 2 over 17 amperes. Okay. If you want to solve for I2, same process. I2 is equal to V1 minus V3 over 2. So that's basically V1 is 89 over 17 minus V3, which is 195 over 17 all over 2. So we will get negative 53 over 17. Okay. And we have I3 is equal to um, V2 over 3. So that's V2 over 3 is equal to 89, 87 over 17 over 3. So that's basically 29 over 17. All right. And for I4, we have I4 is equal to tail V2 minus head minus V3 over 4. So that's V2 is 89 over 17 minus V3, which is 195 over 17 over 4. So that's basically I4 is equal to negative 27 over 17, right? So we have our I5 finally equal to, that's V3 over 5. Alright, so V3 is 195 over 17 over 5. So that's basically 39 over 17 amperes. So we have all branch currents from I1 to I5, but notice that um, I1, I3, and I5 are positive currents, while I2 and I4 right here, I2 and I4 right here are negative currents. So this one and this one. I will explain this one. All right, let's now analyze our answers. We already have calculated the current for each branch of the network. So we found out that um, I1, I3, and I5 are positive currents, while I2 and I4 are negative currents. What does it mean? So when we assume directions for I1, I2, I3, I4, and I5 previously, we are actually at risk of getting um, wrong direction of current. Okay, so in this example, we uh, the direction of our assumed directions for R1, I1, I3, and I5 are actually correct. So meaning this the current or the current is actually flowing from V1 to V2, then uh, V2 to the reference node, and V3 to the reference node. These are correct flows of current I1, I3, and I5. However, for I2, this right here, the assumption that the current is going from V1 to V3 is wrong, because what is correct is the other way around. So meaning your I2 is actually going in that direction, the opposite direction. And so with your I4, in this part of the network, your current is actually going from V2 to, I mean from V3 to V2. Okay? So we can redraw the circuit. We can redraw the circuit and analyze and see if our answers are uh, correct. Okay, so of course we have our V1 here, we have our V2 here, we have our V3 here. Okay, so we have correct currents for I1. So this is I1. Okay, I1. We have our I3 here. This is also correct direction. I3 downward. We have our I5 here. This is also correct direction downward. Now for I2, the previous direction is to the right. So we get a negative current. So actually our I2 is the opposite direction. This is our I2. Okay? Okay? Then our I4 is not to the right but to the left also. Okay? So this is our I4. Now with this new current direction, we can say our I1 is actually 2 over 17 ampere. Our I2 is equal to 53 over 17 ampere, and our I3 is equal to 29 over 17 ampere. Notice we have I4 also, that is 27 over 17 ampere, and I5 which is equal to 39 over 17 ampere. Okay, so notice there is no negative currents here. Why? Because I already changed the direction in the diagram. Now if we try to check, for example, this node, right here, sum of current entering should be equal to sum of current leaving. So this is one way of making good feeling, a good feeling that your answer is correct. So you check, uh, you do your KCL here. So it has to be entering equals leaving. So what is entering is I2, so that's 53 over 17. Is it equal to the currents 3 plus I1? So 3 plus your I1 is 2 over 17. Of course, 3 plus 2 over 17 is 53 over 17. Of course. So this is correct. If you try it here also, so say I'll use this one. So if you try at this node also, if you try it here, so entering, what's entering here is 7 ampere. So that's 7, and everything is leaving. Is it equal to the current I2 plus I4 plus I5? You can check. So that's, is it 7? Is it equal to I2, which is positive now because I have changed the direction, plus I4, which is 27 over 17, plus I5, which is 39 over 17. If you use your calculator, you will get this number here equal to 7. And so with this part of the network. Okay, so this is one way of making a good grasp, making a good feeling that your answers are correct. And I'll do this all the time since I know circuit analysis way back 20 years ago. Okay, and that's it for this video, everyone. Please watch out for my next video and please support my channel. Thank you once again.